In this video, we will align and perform the quantum eraser experiment using the Quantum Optics Educational Kit. To begin, take the 1-inch polarizer and place it in front of detector T. Ensure the BBO crystal is in the path and switch on the pump laser. Rotate the polarizer and maximize the count rate measured on detector T. If the counts decrease, rotate in the opposite direction or continue rotating through a minimum count rate to the next maximum. Once at the maximum count rate, lock the polarizer with the top screw. Loosen the front screws of the rotation mount. Set the dial to 90 degrees. And re-lock the screws to calibrate the angle of the polarizer's mount to 90 degrees. The next step is to calibrate the 1/2-inch polarizers. Place a spacer between the polarizer and detector T. Place a 1/2-inch polarizer on top of the spacer to make the polarizers the same height. Rotate the 1/2-inch polarizer to minimize the count rate on detector T. Lock the polarizer with the top screw. Loosen the front screws and set the dial on the polarizer mount to 0 degrees. Swap in the other 1/2-inch polarizer and repeat the same process. Since the count rate was minimized, the polarization axis of the 1/2-inch polarizers is now perpendicular to the 1-inch polarizer. The goal is to have the polarizer's transmission axis aligned to the BBO crystal output. The scale should show 90 degrees for a maximum count rate and 0 degrees for a minimum count rate. Next, calibrate the half-wave plate by placing it between the crossed polarizers. Rotate the half-wave plate until the count rate on detector T is minimized. Lock the wave plate with the top screw. And set the dial of the half-wave plate to 0 degrees. When the counts are minimized, the wave plate's optic axis is aligned to one of the polarizer's transmission axes. Switch off the pump laser. Place the half-wave plate in the path between the first beam splitter and the interferometer breadboard with the dial facing the interferometer. Place the alignment laser on the second magnetic base. Switch on the alignment laser. Take the alignment target and place it between the 8mm iris and the first beam splitter so that the alignment laser is passing through the hole. Position the half-wave plate so that the alignment laser passes through the center of the wave plate and rotate the assembly so the back reflection is aligned with the target's hole. It can be helpful to block the interferometer beam splitter with an alignment card to remove reflections from the other elements in the path. Once positioned, fix the wave plate with a clamping fork, screw, and washer. Move the card behind the interferometer beam splitter to block reflections from the interferometer mirror fixed to the breadboard. Position the alignment target after the half-wave plate and ensure the alignment laser passes through the hole in the target. Place one of the half-inch polarizers between the interferometer beam splitter and the mirror on the translation stage, with the dial facing the beam splitter. Rotate the polarizer assembly until the back reflection is aligned with the hole in the alignment target. Secure the polarizer with a clamping fork, screw, and washer. Repeat the same process for the other half-inch polarizer in the interferometer arm. Move the card between the half-inch polarizer and the beam splitter. Place the other half-inch polarizer between the interferometer beam splitter and the mirror fixed to the breadboard with the dial facing the beam splitter. Rotate the polarizer assembly until the back reflection is aligned with the hole in the alignment target. Secure the polarizer with a clamping fork, screw, and washer. Place the screen in front of detector B. Remove the card and alignment target from the path. Position the lens between the wave plate and the interferometer beam splitter. Ensure the laser passes through the beam splitter without being clipped. Interference fringes should now be visible on the screen. Adjusting the stage's manual adjuster or pressing on the interferometer breadboard can help visualize the fringes. Use the adjusters on the mirror mount fixed to the breadboard to center the interference pattern so there is one large fringe. It can be helpful to use one adjuster to create straight line fringes before switching over to the other adjuster to center the fringe. Switch off the alignment laser and remove the lens from the path. Position the LED between the half wave plate and the interferometer beam splitter. Swap the alignment laser USB connector for the LED USB. And ensure the LED output is evenly illuminated on the screen. Use the stage's manual adjuster until interference fringes are seen on the screen. Use the adjusters on the interferometer mirror mount secured to the breadboard to center the fringes. Continue adjusting the mirror and stage adjusters until the contrast is maximized with a single large fringe that blinks with stage travel. Remove the LED and the screen from the path. Return the alignment laser to its original location. Set the half wave plate to 22.5 degrees and re-lock the position with the top screw. The system is now aligned to perform the quantum eraser measurements. Turn on the pump laser and run a Michelson measurement with both polarizers parallel at 0 degrees. Note the range of the y-axis that will be used for each experiment. The resulting interference pattern has a reduced amplitude compared to the previous Michelson experiment without polarizers because half of the photons are absorbed by the polarizers. Interference is seen because the polarization is the same in both arms, so we cannot determine which path the photon travels. This means the photon is in a superposition of both interferometer paths. Now set one of the polarizers to 90 degrees, so that the two polarizer axes are perpendicular to each other, and run another Michelson experiment. In theory, the interference should not be visible. If the y-axis autoscales, there will likely be some interference fringes visible due to the polarization calibration being slightly off. To better compare results, it can be helpful to right-click on the plot and turn off autoscale during the parallel polarizer measurement, or rescale the y-axis to the previous values by clicking on each of the numbers and typing in the previous values. Using the range from the previous experiment shows there is no obvious interference with perpendicular polarizers because there are different polarizations in the interferometer arms. This changes the superposition state of the photon in such a way that measuring the polarization within either arm could reveal which path it traveled, thus removing the interference at the output. For the final experiment, add the quantum eraser polarizer between the interferometer beam splitter and detector B, and secure it with a clamping fork, screw, and washer. Rotate the quantum eraser polarizer to 45 degrees. Rerun the Michelson experiment with the interferometer polarizer still set to 0 degrees and 90 degrees. Interference is visible again, even though we only added a polarizer to the path. Some amplitude was lost due to photons being absorbed by the quantum eraser polarizer, but the interference pattern is still clear. The interference is recovered because the quantum eraser removes the ability to determine which path the photon traveled, so the photon is in a superposition of both interferometer paths when measured at the output polarizer.